Okay, so hello. I hope you are doing well. I'm going to present you the main ideas of my scientific text, which is called Training an Artificial Neural Network using qubits as artificial neurons. So, as you can see, I divided the text into 6 topics where I will explain each of them in the easy way. So I hope that my explications will be clear enough for you. Okay. So why processing data in classical computers could be a problem? The data becomes bigger year after year. It's so bigger that a classical computer must deploy a large number of parameters to analyze how to learn patterns in such data. So here I have represented a zettabyte as a big block of data. And to have an idea on the size of this block is similar to 1 trillion gigabyte. So, which is represented by 1 billion 1 terabyte sized iPads, for example. And we will have 1075 terabyte by 2025. And in fact, some patterns could be too complex for the classical computers to deal with. In this example, we have a chunk of data represented by a kiwi. So let's assume that it contains 175 terabytes. And we ask to the classical computer to analyze it and to tell what the fruit is. And the prediction will be wrong because there is too much data to analyze and so too much patterns to learn. This is why we need to use a quantum computer. So here is the first IBM quantum computer to be installed in Europe in 2021. And here we can see that this prediction is correct. And by the way, a quantum computer can make the detection of the COVID-19 from images. It achieved a high success rate of 9400%. So it's interesting. So what is a qubit state? Because quantum computers use a qubit to deal with the information. So a qubit can be represented by using 0 and 1 states simultaneously. It's called a superposition, whereas the classical bit can be either 0 or 1 state at a time. So if a computer made 2 to the power of k states, classical qubits can be in one of those at a time, whereas the qubits can be in all of those at once. So the superposition here is represented by a state vector of probability. It has the probability for being in state 0 or 1. Well, there is a lot of states on a given of time. But when we see the output of the vector, we can see just one state, and this state is chosen randomly. So, as you can see, the state vector moves from one state to the other state, to the other one, thanks to quantum gates. So, how quantum gates work? Well, conjugate manipulates an input of superpositions, so here, rotates probabilities and produces another superposition as its output. So here we have a clear view of a quantum gate. So for example, we have the XOR gate. So here it's the gate from the classical computer. So we have two inputs, X and Y, and we make the addition with those, and we have only one output at a given of time. And here it's the quantum gate, and we have a superposition as output, another one here, and on the output we have another superpositions. So it's similar to classical computers, but we have a lot of states on a given of time. But sometimes a quantum computer cannot work properly. That occurs when the system is not perfectly isolated from its environment, and it could lead here to decoherence. So, for example, we have an atom who can collide with all those atoms so that the superposition disappears. So the point is that the qubits of the system must be completely isolated from its environment to work properly. Okay. Now that we see how the information can be represented and manipulated by a quantum computer, we're ready to answer the most important question, which is how processing data from the network. Well, to simplify the data analysis, the better is to divide it into artificial neurons represented in a layer called the input layer. And the neurons here are represented by nodes in classical computers, whereas it is represented by qubits in quantum computers. So this guy will tell to another guy that there are neurons to interact with. So we have to do something with them to produce an output. And that is the job of the hidden layer. So this guy here make interaction based on weight connections on nodes, whereas the interaction is based on entanglement on qubits. So that's the difference between nodes in classical computer and qubits in quantum computers. And to do the interaction, we use gates to modify the states. So we have classical gates for nodes and quantum gates for qubits. Okay, we have some new neurons. That's great. But what should we supposed to do with that? Well, we want an output. So we push the neurons to another guy who will produce a corresponding output value. And this guy is called the output layer. So this guy will use an activation function to have the value of the nodes whereas it will measure the states for a qubit. But the guy couldn't be happy with that output value because he compares the output value, also called the prediction value, with the expected output, and he see that it's not good enough. We don't have the output we want. So we call this inequalities an overfitting or underfitting problem. So the output guy asks himself how to resolve it. Well, we have an overfitting because the model is learning too much patterns, and we have an underfitting because the model is not learning enough patterns. So let's take an example. A lemon, a yellow lemon. So we have this lemon in the input of the computer, and well, the computer analyzed the data and produces a green lemon. That's almost the same, but that's not a yellow lemon. So this is because during the procedure some overfitting or underfitting errors occurs. Okay, we figure out why those problems occurs, but how to resolve it? Well, the output guy will return back the neuron to the hidden layer and tells him that, well, there is a problem with the neuron you gave me. Make a direction again. So here we can see this happen here. And this happen while we do not have a good output value. So this procedure is called backpropagation in the classical computer side, whereas it is called hybrid computation in the quantum computer side. So in the first case here, we optimize the parameters of the nodes, and in the second case here, we optimize the rational parameters of the qubits with classical computations on the classical computer. Okay. Well, we can ask ourselves, is the quantum computing a really good approach? Well, we have two experimental evaluations here, both on classical computers and quantum computers. So, in a certain model, of course. Here we have the Adam model. So, despite the first graph tells us that the training cost is bigger than a classical computer, we can see on the second graph that the quantum computing approach for training an artificial neural network on a quantum computer is much better than an artificial neural network on a classical computer. Here we have a better accuracy. Okay, that's all for my presentation. I hope that I haven't lost you, because quantum computers are very complex to understand, but I think that someday it will replace our classical computers. So have a good weekend. Goodbye.